Hello everyone, my name is Pranav Mundada. I will talk about the recent results on Floquet engineering from the Houck lab at Princeton University. There has been a tremendous progress in the coherence values achieved in a fluxonium qubit. However, it is not possible to achieve simultaneous T1 and T2 protection for a given flux bias point. For example, away from half flux bias point, one can get disjoint wave functions leading to high T1 values, but there is no T2 protection here. At half flux bias point, the two wave functions hybridize, leading to insensitivity to the external flux bias and high T2 numbers, but there is no T1 protection here. Ideally, in a qubit, we want simultaneous T1 and T2 protection for high performance. So we want our wave functions to be simultaneously disjoint and delocalized. In 1D, it is not possible to do this. However, in 2D, one can achieve simultaneous delocalization in one axis and disjointness in the other axis. One such qubit is a 0-pi qubit, which was proposed by Brooks, Kitaev, and Preskill in 2013. This has finally been realized in the Houck lab last year in our experiments. The results can be found on this arXiv paper. Now the question is, can one get similar kind of protection by adding a periodic drive to the system? This can be thought of to make the system a 1D in space plus a 1D in time, leading to Floquet states. This is the Hamiltonian for a fluxonium qubit. Now let's bias it near half flux quanta and add an additional periodic drive of flux through the loop. The system can now be modeled as a two-level system as follows, and our goal now is to check if we can achieve sweet spots away from half flux bias. We are going to consider the following parameters for our fluxonium qubit henceforth. For an undriven fluxonium qubit, the eigenenergies have an avoided crossing at half flux bias point, which gives a sweet spot. The transitions observed in the spectroscopic measurements for this system are shown below. When the Floquet drive is turned on, the energy dispersion of the qubit is modified, giving sweet spots away from the half flux bias point. Here is the experimental data from a light fluxonium device. At half flux sweet spot, we get a T2 Ramsey of 76 microseconds and an echo time of 120 microseconds, whereas away from half flux sweet spot, we get a T2 Ramsey of only 0.6 microseconds and T2 echo of about 5 microseconds. This is the spectroscopy mapping of the energy levels for a bare fluxonium qubit. As a weak Floquet drive is turned on, one can see that there are copies of the energy spectra separated by the drive frequency. This corresponds to the Floquet states expected from the previous theory. Our spectroscopy measurements show two types of dynamical sweet spots away from the half flux bias point. First is the DC sweet spot, which gives insensitivity to fluctuations in the DC flux bias. The AC sweet spot gives insensitivity to the fluctuations in the amplitude of the modulation drive. The existence of these two sweet spots gives rise to complete insensitivity to any external flux perturbations. Now let's look at the dephasing times obtained for a Floquet drive for different modulation frequency and drive strengths. Considering only DC flux noise, one gets this kind of sweet regions where the system is insensitive to fluctuations in the DC flux bias. Similarly, the system has different sweet curves for insensitivity to the fluctuations in the amplitude of the Floquet drive. Effectively, there are certain regions in this parameter space of modulation frequency and modulation strength, where one can achieve simultaneous AC and DC sweet spots. Turning on flux modulation reduces the T1 of the system to 26 microsecond, which is about 3.5 times lesser than the static case. However, there is a big improvement in the T2 Ramsey data for Floquet qubit. Depending on the modulation frequency and the modulation strength, one can achieve as high as 25 microsecond T2 Ramsey data for the fluxonium qubit away from half sweet spot. This is a 40x improvement compared to the static case. In summary, we have achieved a 40x improvement on our Ramsey measurements for a trade-off of 3.5x in T1 decay. We are currently limited by AC10F noise in our flux modulation. For future work, we would like to reduce this AC noise and explore multi-tone drives for enhanced insensitivity to AC noise. I would like to thank Andras Genish, who worked on the experiments with me, our PI Andrew Hauk, our theory collaborators Xuan Huang and Jens Koch for excellent support on this project.